Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to tackle a practice problem set that relates to our lecture on carboxylic acid derivatives. Let's go ahead and get started with problem number 1. Problem number 1 says, which of the following would be the best method of producing methylpropanoate? The first step is to draw out the structure of the goal product. This molecule, you'll notice, is an ester, meaning it contains a carbonyl group directly bonded to an oxygen atom, which is in turn bonded to a carbon chain. Once we recognize that the goal is to produce an ester, we should recall how esters are made. Esters are typically made by reacting a carboxylic acid with an alcohol under acidic conditions, and this is a process known as Fischer esterification. To figure out exactly which carboxylic acid and alcohol we need, we can break the ester bond mentally. So to do this, we cut the bond between the carbonyl carbon and the oxygen atom. Then on the carbonyl side, we are going to add a OH group. So that is going to generate the carboxylic acid we need. Then on the oxygen side, we're going to add a hydrogen atom to generate the alcohol that we need. So after making this cut, we can see that the carbonyl side becomes propanoic acid and the oxygen side becomes methanol. So to generate methylpropanoate, we need to react propanoic acid with methanol in the presence of an acid catalyst. Now, looking at the answer choices, answer choice A describes exactly this, reacting propanoic acid and methanol in the presence of a mineral acid. Let's move on to problem 2. Problem 2 says, what would be the products of the reaction below? First, let's start by identifying the structure that's provided. The structure is a simple anhydride. More specifically, it's acetic anhydride. So it's made up of 2 acetyl groups that are connected by an oxygen atom. Now, when you see an anhydride reacting with a nucleophile like ammonia, you should immediately think of a nucleophilic acyl substitution reaction. Ammonia is going to act as the nucleophile here, and it's going to attack the carbonyl carbon of one of the carbonyl groups in the anhydride. The electrons from the carbonyl double bond are then pushed up onto the oxygen atom, and we're going to temporarily form a tetrahedral intermediate. Next, that tetrahedral intermediate is going to collapse, so the carbonyl double bond reforms, and the leaving group is going to be the remaining carboxylate part of the anhydride. So as a result, this is the part you need to know, the immediate products we form are one molecule of an amide, where ammonia has replaced the oxygen connection, and one molecule of a carboxylic acid that's derived from the other half of the anhydride. But we're not quite finished yet. Because ammonia is present in the reaction mixture, and because a carboxylic acid is produced, we're going to have an acid-base reaction that follows immediately. So the newly formed carboxylic acid, being acidic, will donate a proton to the basic ammonia molecule. And this is going to create an ammonium ion and the deprotonated form of the acid, which is the carboxylate anion. So the final products of the reaction are going to be an amide and an ammonium carboxylate salt. So looking at the answer choices, choice D matches exactly what we just determined. One molecule of an amide and one molecule of an ammonium carboxylate. So 2 is D. Moving on to problem 3, which of the following undergoes a Fischer esterification more rapidly? In a Fischer esterification, A carboxylic acid reacts with an alcohol under acidic conditions to form an ester. The key step is that the alcohol must attack the carbonyl carbon of the carboxylic acid. Therefore, the rate of Fischer esterification depends heavily on how accessible that carbonyl carbon is to nucleophilic attack. If there's a lot of steric hindrance, meaning bulky groups that are surrounding the carbonyl carbon, then the reaction is going to be slower. But if the carbonyl is more exposed and less hindered, then the reaction will be faster. So with that in mind, let's look carefully at the structures given. In choice A, we see a simple carboxylic acid where the carbonyl carbon is attached to a 2-carbon chain with no additional branches. So there's no bulky groups next to the carbonyl carbon, and that means that carbonyl is very accessible for attack by an alcohol nucleophile. Looking at choice B, we see a carboxylic acid where the carbonyl carbon is attached to a secondary carbon. So this is a carbon that is already bonded to 2 other carbon groups. This increases steric hindrance around that carbonyl. Then in choice C, we see an even more crowded structure. This is a tertiary carbon. So the carbonyl is directly bonded to a carbon that has 3 other carbon groups. This creates significant steric hindrance, and that makes nucleophilic attack much more difficult. Then, in answer choice D, we see the most crowded structure of all. The carbonyl carbon is attached to a carbon that itself is bonded to 3 ethyl groups. This heavy steric bulk severely limits accessibility to the carbonyl carbon. Therefore, based on steric hindrance alone, structure A will undergo Fischer esterification the fastest because it has the least steric hindrance. Now, it's also important to point out that there is a second factor to consider, and that is electron donating groups. When alkyl groups are attached near a carbonyl carbon, they're going to donate electron density through inductive effects. And this makes the carbonyl carbon less electrophilic and less reactive towards nucleophilic attack. Structures B, C, and D are not only more sterically hindered, but they are also less electrophilic compared to choice A. So both steric hindrance and electronic effects favor A as the fastest reacting compound. So 3 is A. Problem 4 says, each of the acyl compounds listed below contains 6-membered rings except blank. Let's work through the options here, starting with choice A delta-lactam. A delta-lactam forms a 6-membered ring because the ring includes the carbonyl carbon, the nitrogen atom, and 4 carbon atoms. So that gives us a total of 6 atoms. Choice A has a 6-membered ring. Choice B is a cyclohexane carboxylic acid. Cyclohexane is a 6-carbon ring by definition. The carboxylic acid group is attached outside of the ring, so the ring still remains 6-membered. So choice B is also a 6-membered ring. Choice C is a gamma butyrolactone. When you're drawing or visualizing this molecule, the ring contains only 4 atoms, the carbonyl carbon, an oxygen atom, and 2 carbon atoms. So this choice actually forms a 4-membered ring, not a 6-membered ring. So C is going to be the correct answer here, but we're still going to work through D. Choice D says the anhydride formed from intramolecular ring closure of pentane-dioic acid. So drawing this out, pentane-dioic acid is going to have 5 carbon atoms, and when the 2 carboxylic groups react to form a cyclic anhydride, the ring formed includes the 5 carbons, and 1 oxygen, which totals 6 atoms. So choice D also has a 6-membered ring. The only structure that does not form a 6-membered ring is choice C. So let's move on to problem 5. Problem 5 says, which of the following would be most reactive towards nucleophiles? Looking at the answer choices, we notice that we're comparing an ester, a carboxylic acid, an amide, and an anhydride. To determine which compound is most reactive towards nucleophiles, we're going to focus on 2 factors: how electrophilic the carbonyl carbon is, and how good the leaving group is. Amides are going to be the least reactive. The nitrogen donates electron density into the carbonyl through resonance, and that makes the carbon less electrophilic and harder to attack. In addition, the leaving group is also poor. Carboxylic acids are next. The hydroxyl group doesn't leave easily, and the molecule is stabilized by hydrogen bonding. Then esters are moderately reactive. The alkoxy group is a better leaving group than hydroxide, and there's less resonance stabilization than in an amide. Finally, anhydrides are the most reactive. So the leaving group is a carboxylate, which is resonance stabilized and relatively stable on its own, and this makes the carbonyl highly susceptible to nucleophilic attack. So based on electronic effects and leaving group ability, the most reactive compound towards nucleophiles is the anhydride. So 5 is D. Problem 6 says, how might succinic anhydride, shown below, be formed from succinic acid, aka butane-dioic acid? The structure that's shown here is a 5-membered ring with 2 carbonyl groups that are connected by an oxygen atom. This tells us that we're forming a cyclic anhydride from a dicarboxylic acid. When 2 carboxylic acid groups are on the same molecule and they're positioned close enough, they can actually react with each other to eliminate water and form a ring. This is an intramolecular condensation reaction. For this kind of reaction, no external reagents are needed, just heat. Heating drives off a molecule of water, which causes the 2 carboxyl groups to join and form the cyclic anhydride. So the correct condition for this transformation is heat, which corresponds to answer choice C. Problem 7 says, which of the following would react most readily with a carboxylic acid to form an amide? To answer this, we need to think about how amides are formed. A carboxylic acid is going to react with a nucleophilic amine, and during this process, water is eliminated. And for this reaction to proceed efficiently, the amine must be nucleophilic enough to attack the carbonyl carbon and not too sterically hindered, so it can approach the reactive site. So let's focus on these 2 factors, nucleophilicity and steric hindrance. In answer choice A, we have methylamine. This is a primary amine with minimal steric bulk. It's going to have a lone pair on nitrogen, and it can easily donate that pair to the electrophilic carbonyl carbon of the acid. This makes it both highly nucleophilic and physically unhindered. So that's pretty ideal for forming an amide. B says triethylamine. This is a tertiary amine, and although it has a lone pair, it's very hindered by 3 bulky ethyl groups. So this makes it poor at directly attacking carbonyl groups. C says diphenylamine. This has 2 bulky aromatic groups, and those electron-rich rings can also delocalize the lone pair on nitrogen. So that's going to make it less nucleophilic and less reactive towards acids. Finally, answer choice D says ethylmethylamine. This is a secondary amine. It can form amides, but compared to answer choice A, it has slightly more steric hindrance. So overall, the amine that reacts most readily with a carboxylic acid is going to be methylamine, which is choice A. Problem 8 says, if propanamide were treated with water, what products would be observed? Propanamide is an amide, and amides can undergo hydrolysis to yield carboxylic acids. But this reaction, it doesn't occur readily under neutral conditions. Amide hydrolysis typically requires a strong acid or a strong base, along with heat to proceed at a significant rate. If no such conditions are specified, and we're just mixing propanamide with water, then the reaction won't actually proceed to completion, because water alone isn't reactive enough to break the amide bond on its own. So under these mild conditions, no reactions occur, and the only species we'd observe in solution is the starting material, which is propanamide. So the correct answer for problem 8 is A. Let's move on to problem 9. Problem 9 says beta-lactams are blank. Statement 1 says cyclic forms of the least reactive type of carboxylic acid derivative. Statement 2 says more reactive than their straight chain counterparts. And statement 3 says molecules with high levels of ring strain. So first and foremost, beta-lactams are a type of amide, and amides are generally the least reactive carboxylic acid derivatives. So this makes statement 1 true. But here's where structure changes reactivity. In the beta-lactam, the nitrogen is part of a 4-membered ring, which introduces a significant amount of ring strain. The carbon-nitrogen bond in a normal amide, it's going to have partial double bond character due to resonance. But in a strained ring, that resonance is reduced, and that makes the carbonyl more electrophilic, and it makes the bond easier to break. So despite being an amide, the ring strain makes beta-lactams much more reactive than their straight chain counterparts. So statement 2 and statement 3 are both true. So all in all 3 statements are correct, and problem 9 is D. Problem 10 says, the acid catalyzed conversion of propyl ethanoate to benzyl ethanoate is likely blank. From the name, we can recognize the structure. Propyl ethanoate is an ester, and it has an ethanoate group bonded to a propyl group. The product, benzyl ethanoate, is still an ester, but the alcohol part has changed. Now it's a benzyl group instead of a propyl group. This tells us that the carbonyl portion of the molecule is unchanged, and only the alkyl group bonded through the oxygen has been swapped. So this points to a transesterification reaction, which is an acid-catalyzed process where one alcohol group in an ester is replaced with another alcohol. The ester stays intact, but the alcohol-derived portion changes. So 10 is C. Problem 11 says, the reaction shown, which is important for the breakdown of polypeptides, would be favored under what conditions? We're shown a reaction in which an amide is being converted into a carboxylic acid and an amine. This is a hydrolysis reaction, specifically the hydrolysis of an amide bond. And this process is biologically important because it mimics the way peptide bonds are broken in polypeptides. In this case, water is the nucleophile. The amide carbonyl is electrophilic, but not very reactive on its own. So to promote this reaction, we need to activate the carbonyl and make it more susceptible to nucleophilic attack. That's where the acidic conditions come in. Acid can protonate the carbonyl oxygen, increasing the partial positive charge on the carbonyl carbon and making it more electrophilic. And this is going to facilitate nucleophilic attack by water, which leads to cleavage of the amide bond and formation of a carboxylic acid and an amine or ammonia. So the conditions that favor this reaction is an acidic environment, which is choice B. Problem 12 says, a positive charge on the molecule shown would have greater stability than a positive charge on a straight chain alkane version of the small molecule. What property explains this effect? In the structure that we're given, we have an aromatic ring that's attached to a carbonyl group, which is further attached to an amine. The benzene ring here is going to play a very important role. What makes this molecule special is the presence of conjugation. Conjugation refers to the overlap of adjacent p orbitals that allows for the delocalization of electrons across multiple atoms. So it's this alternating double bond, single bond, double bond, single bond that allows for electrons to be delocalized. So in this case, if a positive charge were placed anywhere on the system, the electrons in the pi system of the benzene ring and the lone pair on the nitrogen can help stabilize that charge by delocalizing it through resonance. A straight chain alkane isn't going to be able to offer any of that stabilization because there are no pi electrons or conjugated systems to delocalize the charge. So the property that explains the increased stability of the charged molecule shown compared to a non-conjugated counterpart is conjugation. So 12 is D. Problem 13 says, the molecule shown is blank. Statement 1 says, the molecule is synthesizable from a gamma hydroxycarboxylic acid. Statement 2 says a lactone, and statement 3 says a form of an ester. Let's start with thinking about statement 1. To assess this, we need to think about how lactones are formed. Lactones are cyclic esters that typically form from hydroxycarboxylic acids through an intramolecular reaction. In this structure, we see a 5-membered ring that includes a carbonyl and an oxygen atom as part of the ring, which suggests that the molecule came from a hydroxy acid. Specifically, for a 5-membered ring to form, the hydroxyl group must be on the carbon that is 3 atoms away from the carboxylic acid. That is the gamma position. So statement 1 is true. For statement 2, a lactone is defined as a cyclic ester, and we just pointed out that the structure here shows a 5-membered ring that contains both a carbonyl and an ether oxygen in the ring, and that fits the definition of a lactone perfectly. So statement 2 is also true. Finally, for statement 3, even though this isn't a linear ester, a lactone still contains the ester functional group, so statement 3 is true as well. Since all 3 statements are correct, the answer is D. Problem 14 says, which reactant could be combined with butanol to form butyl acetate? The name tells us everything we need to identify the reactants. Butyl comes from butanol, and acetate refers to the acetic acid portion of the ester. So to make butyl acetate, we need to react butanol with a molecule that provides the acetic acid part, specifically the group CH3CO. That means we need a compound that contains 2 of these groups derived from acetic acid. And that's exactly what we see in answer choice A. This is known as acetic anhydride. And anhydrides are reactive towards alcohols, and in the presence of catalytic acid, they can form esters. They can react to form esters. So when acetic anhydride reacts with butanol in the presence of acid, we form butyl acetate and acetic acid as a byproduct. So that makes answer choice A the correct answer. Choices C and D are amides, which are not reactive enough under these conditions to form esters. And choice B uses a different anhydride, which would give you butyl propanoate, not butyl acetate. With that, we move into our last and final problem for this video. Problem 15 says, why should esterification reactions not be carried out in water? Answer choice A says carboxylic acids, from which esters are made, are generally insoluble in water. B says the polar nature of the water overshadows the polar nature of the leaving group. C says the extensive hydrogen bonding of water interferes with the nucleophilic addition mechanisms. And D says water molecules would hydrolyze the desired products back into the parent carboxylic acid. So to answer this, we really do need to think about esterification and what it produces. This is a condensation reaction between a carboxylic acid and an alcohol, typically catalyzed by an acid, and the byproduct of this reaction is water. Now, if water is a byproduct, then adding more water to the system would drive the reaction in reverse, according to Le Chatelier's principle. Instead of moving forward to form more ester, the water would shift the equilibrium back towards the carboxylic acid and alcohol, which are the starting materials. In fact, the reverse reaction has a name, hydrolysis. Water molecules, they can attack the ester and break it back down into the original carboxylic acid and alcohol. So performing an esterification in the presence of excess water would actually reduce the overall yield of the ester. So that means the correct answer here is D. And with that, we've completed this practice problem set. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.